Welcome to Network Engineering. This is Chapter 4, Part 2, where we do a deep dive into the Internet Protocol. So the Internet Protocol was developed back in 1978 to support the emerging ARPANET, which was the first inkling of an Internet. And it was developed by this fellow named Vint Cerf, and it very quickly kind of grew and spiraled into this thing called IP version 4. IP is still the basis for layer 3 of the internet's layer cake. It is the layer that gives us the ability to route traffic through these virtual packet switch networks that Vint Cerf developed. And when IP4 first hit the scene in 1983, there weren't that many computers. No one believed that there would be that many computers. The microcomputer revolution hadn't really taken off yet. And so IP4 allowed for 32-bit addresses, allowing for 4 billion internet addresses, which just doesn't seem like a lot today, given how many iPhones Apple sells. But back then, it was just mind-boggling, right? So we knew back in the 90s that we were going to run out of address space, and that motivated the development of a replacement. And that replacement is IP version 6. And instead of just going from 32 to 64-bit, we go all the way from 32-bit to 128-bit. And this allows us to go from 4 billion addresses to some ginormous 3.4 times 10 to the 38 addresses. That's just kind of crazy talk, like how big that really is. We could actually give every grain of sand on the planet a unique IP address and still have a large number to spare. As another layer in the layer cake, just as we've seen with all of the other layers in the layer cake, we're seeing encapsulation. And so what's going to happen is this is the header. Whoa. Need my pen. So this is the header for an IP version 4 packet. And if we had like TCP data, it's going to get stuffed in here. So this is just another one of those encapsulation schemes where we're going to take whatever we get from the upper layer, stuff it into the data section of this header, and mail it on. So if I had a block of data, say from a web server, so we have an HTTP value, it's going to get wrapped. I shouldn't draw it that way. Let's draw it this way. It's going to get wrapped in a TCP header and then given over to IP. The IP protocol is going to add its header, and then this is the data section for that. Just like this was in the data section for the TCP block. And IP is then going to send it out over another lower layer, a physical layer. And so that link layer may end up having its own header as well. So we'll see later on that there's going to be an Ethernet header. And all of this stuff just becomes the data section for that. So everything just gets wrapped. So that's what we're going to see. We'll go through these fields again on a later slide, but I just want to kind of contextualize where we are with all of these different layers and stacks and the game of who's got the data today. The Internet Protocol allows for a number of different addressing methods, and the most basic one here is this Unicast. So I have one sender sending to one receiver, and somehow the internet is going to allow me to send this message out and find a path to get to that one guy. And so we call that Unicast. It is a one-to-one addressing, one sender, one receiver. We can also talk about broadcast, and a broadcast is going to be a single datagram that goes to everybody on some broadcast domain. We've already seen in the last section that we had collision domains, and we're going to add now to the idea of a broadcast domain. And in most places, those are going to be the same thing. So what's going to happen is I send out a broadcast, and the domain that we're talking about is going to be my local network. The routers don't typically route broadcast messages onto the next hops. So it may be that the collision domain equals the broadcast domain, but that's not a requirement. Routers could forward broadcast messages to other LAN segments, for instance. A multicast message is one where we're going to send the message out from one sender, and it's going to be given to a group of receivers that have that multicast address configured. And so it may be that I'm going to listen for those incoming messages on these special multicast addresses, and I'll pay attention to them, and other ones I'm just going to ignore, right? So this is good for video streaming. For instance, if you have like a video camera and you want to be able to have a bunch of security feeds, and you want multiple viewing stations, you don't want to have the camera, which may already be struggling just to keep up with capturing video and sending it out over the wire. You don't want the camera having to send it out like 50 times. You just want to be able to have the camera send it out once over your network, and then have the 50 receivers just listening to that multicast address, and then they can all watch the stream coming in. Unicast is part of IP6, and in Unicast what we're saying is I can send a message from one sender to one receiver, but I don't care which receiver gets them. So in Unicast, the routing hardware is able to make a decision that maybe this is the best route for that sender. Maybe this sender sends to the same Unicast address, and for some reason it decides that that's also the best one, even though those two look like they might be closer together. This one might send to that, and that one might send to that. So it's possible that just based on the routing, that with Unicast, we could actually have traffic going to the same Unicast address but go to completely different hosts. This would be phenomenal for things like content servers, where I don't care which Netflix content server I pull my next block of data from. Let the routing decision happen and find the best one for me. And so that's new in IP6, and it's a really useful addition to the protocol in my mind. Geocached is not part of any of the land-based protocols today. It is much easier to implement over wireless, right? So I can have a single antenna sending out messages and eventually getting down to one guy with the phone in his hand, right? And if you're within range of that tower, you'll get the message, but if you're the guy with the phone out of range of that tower, you won't get the message. So Geocast has a natural broadcast capability to it, just because radio signals only work in a certain range. We're hoping to be able to develop something similar for land-based devices. So for instance, an emergency tornado alert needs to be sent out to everybody in a certain zip code. And that could go to your internet connected TVs, your computer messages, your smartphones, whatever device you happen to be looking could actually get that message. So anyway, so that's like the goal, but Geocast is kind of in development. We just haven't gotten there yet. All right, let's take a look at the IP version 4 header. And when IP version 4 came out, it was much more important to limit the size of these things than it was to make them easy to process. And so what we're going to find is that the headers here can be of variable length. And it makes it much more difficult for routing hardware to be able to find values in a variable length field. just because, for instance, I can have 0 options in here, or I can have many. And so when I'm looking for the TCP data, how do I know where to find it? Well, I actually have to do some arithmetic and figure it out. I mean, we can do it. It's just not as nearly as efficient as what we'll see later on with IP6. So, based on what we've got going on here, we have a version number. And the version number is going to tell us what version of the protocol this is. It would make sense that it's 4, but I don't think it is. I think it's like, I'm not even going to say. There is a version number. I know IP6 is 6, but I don't think version 4 is 4. Header length. So this is going to tell us where the payload begins. I believe it is in, because it's only 4 bits. So 4 bits would only give you 16 bytes. And with 16 bytes, let's see, if this is byte 0, this would be byte 4, because this is all 32-bit, byte 8, byte 12, byte 16. It doesn't even get you through the end of the IP packet, the required stuff. So I'm pretty confident that this is in terms of words, not bytes. And so that lets me have an IP packet that could go from 0 times 2 to the 3rd, 2 squared, up to 15 times 2 squared. So this could be 0, 2, and this would be 4. So 15 times 4 is 60. So now, if the packet can't be 0 bytes, obviously, everything in here is fixed except for the options. So that gives us 1, 2, 3, 4, 5 words at a minimum. So at a minimum, we're looking at 20 bytes. And it could be anywhere between 20 and 60 bytes, just to do some simple math based on having that 4-bit header. All right. And again, those variable packets are kind of a pain. We're going to have an indicator for the type of service. And we'll see later on that type of service is also part of the explicit congestion notification. And so we'll see that we can use this for specifying like the quality of service that we need for this packet. It's what we request. It doesn't mean that we'll definitely get it. Datagram length, this is a 16-bit value, and this is going to tell you how big this section can be. And again, as a 16-bit value, that gives me 2 to the 16 minus 1 is my biggest size. And so I could have a datagram length of up to 64K. That's the biggest it can be. If I need to send a meg, we know it's going to have to go out in multiple fragments. Very rarely, though, do we actually see the datagram length get that big. It's typically going to be 1,000, 1,500 bytes, because that's the natural size of the next layer down. The next guys here, the ID, the flags, and the fragment, are all part of the reordering out of order delivery process for IP. So what's going to happen is each new datagram that gets sent out with an IP packet is going to have a unique identifier, and we're going to be able to say, okay, this is packet number 500, and this is fragment number 0 says that this is the first fragment, and then we're going to say that's fragment offset 0, and then the next one's going to be this is not the last fragment, not the first fragment, it's offset 100 or whatever the number of bytes are. And what will happen is the routers can read these things and reorganize all of these received IP datagrams with all of their source data into one TCP packet, and then hand it back to the TCP layer as one unit. or the TCP will time out and we'll start the retransmit cycle that we learned about in the last chapter. One of the things that we learned the hard way, we do not want to have a packet living on the network forever. You could imagine what would happen if I sent out a datagram that somehow routed to router A, and then it routed back to router B, and then routed A, and router B, and router A. It would just live forever. And if we had a whole series of those, eventually the whole internet would just fall apart with circuitously routed packets. So to fix that, we put a time to live on all packets. And it can only be up to 8 bits. So at most, we get 256 hops through the network. So every time a router picks up a packet and forwards it, it's going to decrement the time to live value of this IP packet. And if you haven't figured out by now, yes, every router is free to rewrite these IP packet or IP datagrams as it forwards them. And so we don't typically, with switching just cut through switching, it's going to connect the input to the output and there's no changes made. Even with store and forward and switching, we typically don't change the values that were received. The switch just picks up the packet, puts it in memory, and then delivers it out to the remote device right from memory. Here, routers are going to be modifying each of these. For instance, the routers are going to perhaps fragment up a received datagram. And so when it decides to forward a big datagram over a link that can't handle that size, it'll just carve it up into multiple pieces and update the fragmentation information. Likewise, every time it forwards a packet, it's going to decrement this time to live field, and when that time to live field gets to 0, the packet gets dropped. And then it's dead. The upper layer protocol is used to figure out who gets the IP data, the data from the datagram once it's received. Yeah, technically we could probably look at the data, and I think there's if I recall, there's a header for TCP and there's a different header for UDP, and we could figure that out. But let's just make that easy to figure, right? So we don't want to have somebody else's service that happens to just randomly match the beginning of a TCP service. We just want to say this is TCP. There are many other protocols that could be in here than TCP and UDP. We haven't seen them yet, but I give you a link to the Wikipedia page that you can go find them if you're interested. As we saw in TCP and UDP, we have the same ones complement checksum. And so we'll see the same checksum for the header. And again, there's a demand placed on the router to verify that the header checksum matches the computed checksum. And if they don't, the packet gets dropped. But that does put more processing burden on the router. The really interesting ones are going to be these source address and destination address. And as I said before, these are each 32-bit. And so we'll be able to make our routing decisions based on those addresses. And we've already kind of seen that, but we'll do a much deeper dive into the routing decisions. Finally, we can have, like as I said, 0 or more options. And then once we've gone through those options, we'll finally have the payload data for whatever protocol we were encoding. So that's the IP4 header in all of its glory. IP fragmentation, as I said, is kind of handled by the routers. A large IP packet may have to be chunked up. For instance, layer 2 has a maximum transition unit, and if we try to send anything greater than this, it's going to have to be sent as multiple IP packets. The one really challenging thing about IP4 is that every router on a path may be using different technology and have different MTUs. So for instance, certain fiber optic networks have very tiny MTU networks so that we can maximize the performance of those high-speed networks. But that means that we're going to have to break these IP packets up into really tiny chunks. And so it you just don't know until you see the path that it follows. And what's really crazy is that the packet can be split up into multiple fragments by the routers, but then it has to be reassembled by the receiving routers. And we need to be able to do that kind of transparently. In other words, I don't get to see that process. I get to see right through it. So on transmit, the sender is going to stamp. So this is your program, or your operating system. When it issues an IP datagram onto the network, it puts a stamp that says this is a unique packet. It stuffs the source address and the destination address in. So in some respects, this is a little bit like that TCP sequence number that we saw before. Here's just another way of saying this thing is unique. As long as I have fewer than the number of sequence numbers in flight, so again, this is a 16-bit identifier, so as long as I have less than 2 to the 16th or 64,000 packets in flight at a time, then I can pull off this reassembly. That should be fine. Like, we should never have that many packets kind of working their way through the network at any given time. Although that would be a really interesting thing to try to do. I wonder if it's possible. Anyway, I digress. So the router is going to get this big packet. It's going to split it up into fragments. It's going to add new headers. So it's going to strip off the old IP header and put on a new IP header. And it's going to be taking chunks of the TCP packet along with it. And then there's a flag for all but the last fragment gets that one flag. And if it is, once that last one is received, if we've gotten everything in between, then IP will reassemble and then deliver the frame to whatever the next layer is. This is not like TCP. There is no retransmit if the packets are lost. They're just dropped. And so then this is going to depend on the layer above, whether it be the transport layer to do reliable delivery and issue a retransmit, or the application layer to say, hey, I never got that reply, let me send it again. So, IP is not going to try to do any reliability. It's just going to try to get the data there as best as it can. Okay, so IP addresses are all 32-bit. And I'm going to be honest here. I'm going to go off kind of away from the textbook. The textbook doesn't do a real nice job of talking about these for some reason. And they're all pretty important. Like, fundamentally important. Like, I was really surprised not to find a good discussion of this in the text. So, IP addresses are all 32-bit. And theoretically, we could walk around and talk about whatever number these things are. That's really hard to do. The other thing is that each IP address has a natural hierarchy to it. And so what we're going to want to be able to do is to work with the numbers in a more natural way. So, like, I could go to a calculator and figure out whatever this is in integer form. So I'd have 12 times 16, no, not 16, 256. 256 to the 0 plus 36 times 256 to the 1 plus 160 times 256 squared plus 157 times 256 cubed. And I can tell you right off the bat, this is going to be a number that's about 2 billion. I don't know what it really is. I just know from looking at the binary, that bit sitting in the 31st position, which has turned on 2 to the 31st, and that's 2 billion. And so it's going to be like 2 billion. This is 2, whatever. It's a big ass number. So we just don't want to walk around, and we're going to lose all of the natural hierarchy that we get from IP4. So instead, what we typically are going to do is represent them as what we call the dotted quad decimal form. And in dotted quad decimal form, we're going to have 4 numbers. They're going to be 8-bit numbers each. 4 8-bit numbers is 32 bits. We keep them in decimal this time. Like in comp.org, we often just went straight to the hexadecimal, but in this case, we're going to stay in the decimal. And we just remember that each one of these represents an 8-bit number. So 157 has that binary pattern, 160 has that binary pattern, 36 and 12. And so I could theoretically take any IP address and treat it just as that 32-bit number that it really is. I don't really need to have the dots here. Like, the dots are just for visualization to separate these groups of 4. Likewise, I could turn it into a 4-digit hexadecimal number. And then Sloop's IP address, this is actually Sloop's IP address, would look like that. 9D A0240C. Again, it just doesn't feel as natural for some reason as just using the dotted quad decimal. Each interface on a network card that is connected to the internet needs to have its own IP address. They have to be unique, globally unique. Otherwise, there's no way to get data from one machine to another machine and get it back again. So that would be kind of a fundamental problem. And if a machine has multiple addresses, multiple interfaces, then they would need to have multiple addresses. Now, I referenced the fact that these things have some kind of natural hierarchy, in that if I just treated them as a 32-bit integer, 2 billion some number, I would lose the visualization of what that hierarchy looks like. So let's talk a little bit more about that. So addresses are going to be assigned by this group called IANA. IANA is the Internet Address Number Authority. And it's going to assign a clump of addresses to service providers. So, for instance, IANA years ago provided a clump of addresses to a local organization called EDUCAUSE. EDUCAUSE is the main internet registrar for any .edu in the country. And so they got a clump of addresses, and then Shippensburg University worked with EDUCAUSE to get another subdivision of the range of addresses that were originally given to EDUCAUSE. So we have a range of addresses that all start with 157.160. Everything on our campus starts 157.160. There is no other internet entity in the entire world that has internet addresses of 157.160. anything, just Shippensburg University. And so what this allows us to do is, as far as the world is concerned, they don't need to know how to get to Sloop. They don't care. They just need to know how to get to 157.160. And so what this allows us to have is one external route for the entire campus. And so every machine on our campus gets a 157.160.something.something IP address. And when I send my data out and the remote server says, okay, how do I get back to that machine? I just give it to the server, the router that can handle 157.160. whatever. And in the best effort routing, it will eventually get there. So this natural clumping allows for much more efficient routing, and it allows us to kind of reverse an IP address and at least figure out who it belongs to. I might not know anything about that particular machine, but at least I can ask the internet who was assigned the clump that begins with 157.160. And of course, it's going to come back and say it's Shippensburg University. And in fact, we can do that, I think. Whoa, that's big. So if I use the whois command, I can just type in whois 157.160.0.0, and it comes back and it says, sure enough, the range 157.160 has a range of .0.0 through 157.160.255.255. And 255 is special because that is having all of the bits set. That's like the largest 8-bit value that you can have. So we have the entire range, and we'll talk about the CIDR address coming up. Our net name is ship1-net, and our net assignment is to Shippensburg University. We've had it since 1992. which is really remarkable because, I mean, that even predates me on this campus. Not by much, but I came in the fall of 1993. And one of the things that made me want to come to campus as a student at the time was the fact that they had a real internet connection. We were one of the first of the PASHE schools to have jumped on the internet that early. I can still remember doing a who is on a couple of the schools I was looking at, and SHIP was the only one at the time. So I guess it would be interesting to think what would happen if that hadn't happened. I guess I would be inflicting my wrath on other students. Anyway, all of the rest of this stuff is just the administrative contacts, and so anybody in the world can now say, hey, who's abusing? So let's say that Time Warner Media wants to notify us that someone is violating their copyright. They can do a who is on the IP address that is abusing their copyright, and send an email here to acceptable user policy managers and say, this IP address is sharing all of our movies, please make it stop. And so that's how they can track you down. You know, we can do something similar for another company. Let's just think of somebody like Giant Foods. So I think they're just Giant Foods. So Giant Food Stores. Yeah, so I know Giant was bought by this Dutch firm, Ahold Delhaize, back in the 90s. And so the Giant Foods domain name is actually owned and run by I guess they're in Geneva. But then there are, that's interesting. So you can learn some interesting information about a company and kind of figure out how they are loosely affiliated. And what I don't see here is any kind of IP address information. So what we could then do, if I was really trying to kind of surveil the company, is let's do like an NS lookup and do www.giantfoods.com, and we see they're 165.160.13.20. So now if I do a who is on 165.160.13.20, we can find that that is assigned to this corporation service company. So this is just some kind of third-party internet service provider that Giant's contracted with to run their websites. So if I wanted to do some social engineering, I could just surveil this who is database, and I might actually be able to get pretty far by calling up Giant Foods and saying, hey man, I'm John from the corporation service company, and I'm calling about some weird network traffic that we're seeing, and we just want to know if you're seeing it too, and what can we do about it? You know, I can maybe try to launch a falsification attack against somebody at Giant, and maybe I could actually get into their system that way. I'm not saying that you should. In fact, that's very illegal. I'm just saying that there's a lot of information that's publicly available through these whois databases. And just understanding how network addresses are assigned gives you a lot of information about that company. And we're going to see that it gives us a lot of information about how to manage those IP addresses. So anyway, it's a very powerful concept that we just learned about, and it's one that you're definitely going to want to pay attention to. So what this allows me to do is, as we talked about kind of earlier, is in the SHIP domain now, I have one connection to the outside world, and all the outside world needs to know is the 157.160. And typically we draw the internet as a cloud. Right? I don't know what path it's going to take, but if somebody is sitting out on their home PC and they want to go to SHIP, it's going to find its way through the cloud and eventually get to the route that handles 157.160.anything. And then our router has further subnets on campus. So for instance, if I'm on Sloop, we're going to find that we're on the .36 subnet. And so the router has kind of split up all of the different LAN segments on campus so that, for instance, our School of Engineering subnet is 36, the computer center is 32, the administrative part, like the administrative servers, are on the 28. I think wireless is on the .80. And so there's just a bunch of different subdomains that we can now administer without having to tell the rest of the world that we've done that. So, for instance, when the School of Engineering seceded from the union and we got our own subnet and Tim took over management of that, that didn't require a phone call to everybody's brother about, hey, we have a new route. It didn't change anything once the network administrators put the routes into our router. Okay, so this idea of hierarchical assignment is the basis for packet switching. We don't get to have efficient packet switching if we don't have this hierarchy of IP addressing schemes. So one of the things that we just saw was this thing called the CIDR address, or classes of interdomain routing. And CIDR is a representation for IP addresses that tell you how many bits belong to the network address or the subnet address, and how many bits belong to the local host address. So the format for a CIDR address is going to be like the IP form, the dotted quad, followed by a slash, followed by the number of bits that are comprising the network portion of that. And then the remaining bits are for the hosts, okay? So the reason why we developed this notation is it allows the routing hardware to be easily configured. So for example, to the outside world, all of SHIP's campus has a CIDR address of 157.160.0.0/16. And that 16 says only the first 16 bits of any number, any IP address, are necessary to match it to Shippensburg's campus. And further, what that says is SHIP's campus can have the remaining 32 minus 16 bits worth of host machines. So back in 1992, when they laid out the network, they theoretically could have just made one gigantic LAN for all of campus, and we could have 64,000 computers. And so every computer would be on the same subnet. It turns out that that would have been a really bad decision then, and it would have been a bad decision now. Administratively, it would be very hard to protect access to resources, and it would be really hard to administer. It would be very bad performance. It just would not be a good situation. So instead, what we've done is we have subdivided the campus. So if you're on campus, your CIDR address is a 22. So outside world, we're a /16, and that's what IANA and EDUCAUSE assigned to us. On campus, all of our addresses have 22 bits of network address. 22 bits is not going to get us right on one of those dotted quad boundaries, right? So if it was a 24-bit, 24, 16, I guess 32, and 8, those are all the natural, like it's going to be, if I was an 8, let me erase this for a second. If this was CIDR address of 8, like 157. Well, it'd be 0.0.0, then only the first quad or the first dotted number would work or be necessary. But we're not that. We're the 16, and that says it's the first 2. Or if I was 24 rather, it would be the first 3. But we're not. We're not 24, we're 22. And so that's when it starts to sink in that maybe it is sometimes better to think about things as binary numbers. So for example, 157.160. We'll do the 32 subnet because it's a nice easy power of 2. 32 in binary is going to be an 8-bit binary. It does not have a 128. It does not have a 64, but it does have a 32. It doesn't have a 16, an 8, a 4, a 2, or a 1. 1, 2, 3, 4, 5, 6, 7, 8. So by saying that we're using a 22-bit long network address says that we have the first 16 bits here, so those don't change. And then I have another, let's see, 22 minus 16 is 6. So 1, 2, 3, 4, 5, 6 bits. All of those bits belong to the same network. That means that I can have 32 belongs to this network. So does 33. So does 34. And so does 35. So in effect, what this allows me to do is to split these guys, these are all going to be the same network number because all of those bits belong to the same subnet that starts with these 6 bits. So for instance, 32.100, that's on that same subnet. 33.205, that's on the same subnet. 34.6 belongs to the same subnet. 35.255 is the last machine on that subnet. That's what dotted quad allows us to that's where a dotted quad doesn't do as good of a job. Like it's hard to kind of think about that without going through and looking at some of the binary arithmetic. Now, let's say just for another example here, let me erase this. Go to a different color. So let's say that instead of that, I had 157.160. whatever. Again, we'll keep the numbers easy. 32. Well, maybe 32 is not as good of a choice because it kind of hides things. Let's go ahead and do the School of Engineering. That's going to be 36. If we had, so let's write this thing out. So these we can stop caring about because those are assigned. Those belong to the whole campus. If we had a CIDR address for the School of Engineering of 24, then the School of Engineering's network would be 36.0. Let's turn this into binary. Well, I don't have to turn it into binary. It's going to be all of those bits. So then the only prefix that would be for the School of Engineering is 36. I would have my first machine at 36.0, my last machine at 36.255. If instead of it being 22, we made it 23, 23 minus 16 is 7 bits. I gotta think, did I do that wrong? 20? Why would it be 23? Oh yeah, so we're gonna have 7 bits of this number as part of the subnet number. So again, 36 in binary. I don't have a 128. I don't have a 64. I do have a 32. I don't have a 16. I don't have an 8. I do have a 4. I don't have a 2. And I don't have a 1. So that's 36 in binary. And what we're saying is 7 of these bits are all part of the same network. And that means that I can have 36.0. So that would be when that bit is a 0, I get 36.0. And I can go all the way up to when this guy's a 1, and then this guy's all filled in over here, and that would be 37.255. So in that case, I would get 512 machines on that network. If the network administrators wanted to really be more conservative, they could actually give us a even shorter subnet address. So let's say, for instance, that I want to have a partial subnet. And so what we're going to do is we're going to take 157.160.36.0 as the base, but we're going to make it a /27. So what this means is I would have all of these bits all part of the subnet, and I would have 3 bits of that number are fixed. So I'd have my 157.160.36, and then in binary 0 is all 0, right? But these first 3 bits are now set rigidly. I can't have any other number there than 0, because that's the number that was given to me, and 27 of those bits are fixed. And so what this allows now is, I have to have one more 0 in there. I have the remaining 5 bits are things I can pick. So I could have all of these be 0, and that would be the 157.160.36.0, and I could go all the way up to a huge whopping, all of these are set to 1s, and that's going to be a 1, a 2, a 4, an 8, and a 16. That's going to be a 36.31. So I would get a total of 32 hosts. And that would be the subnet. If they did that, that would really be like the computer center saying the School of Engineering only needs 32 computers. Well, we need quite a few more than that. But the important thing is, the motivation for this is to make the routing decision easier. The router only needs to store that one CIDR address for every subnet that gets created, and then it's done. So to get to any of the School of Engineering's machines that fall into whatever subnet they've given us, the campus router only needs to have that CIDR entry. So again, Tim could move computers around in the room. It doesn't matter where they are. They get to our subnet because they fall into that IP address range. But if we take the computer out of the School of Engineering and say take it to the math department's on a different subnet. And so our computer wouldn't be able to function on the math department's network without having a new IP address, because it's going to try to use a 157.160.36. something. And when it goes to send data out, the router is going to get a packet from that weird IP address, and it's going to say, well, that's not on my interface. No, I'll forward it anyway. Whoever responds is saying, I'm going to respond to 157.160.36. whatever, and it's going to send it to the School of Engineering subnet, and it's not going to find the computer that asked for it, and it's just going to get dropped. Meanwhile, the computer that we moved up to the math department is going to be asking, hey man, where's my data? It's never going to get the reply back because there's no matching route. And we'll take a look at diagnosing and troubleshooting later on. All right, so CIDR makes it a little bit easier to determine the subnetting that's involved. It's not the only way to do it. We also used to do the old net mask technique. And in the net mask technique, we can mix and match between CIDR and net mask. They're completely interchangeable. If I have a net mask that is, let's say I have a CIDR address of 8, that means I have 8 bits of address that are in my net mask. So that would mean I would have the first 8 bit set. If I had 24 bits, that means I have the first 24-bit set. Sorry, that 250, I shouldn't be using blue, right on a blue line. Where it gets a little bit more interesting is when we have a net mask for something off, like we have here on campus. So on campus, we just saw that we have that /22. It's not a /24. So to get 22 bits turned on, 1, 2, 3, 4, 5, 6, 7, 8, dot, 1, 2, 3, 4, 5, 6, 7, 8, there's 16. And then we had 1, 2, 3, 4, there's 20, 1, 2, 2, 3, 4, 5, 6, 7, 8. So that's the net mask that we would use. And then, let me move this. And then we have another 8 zeros. So the campus net mask of /22, we turn on the first 22 bits, we turn off the remaining 10 bits. So if I were to turn these into decimal, that's easy, 255. That's easy, that's 255. This is not. And so I could go around this in one of two ways. I could look at this and say, well, there's a 128, a 64, a 32, a 16, an 8, and a 4. Add those up in my head to get 252. I didn't really do that in my head, by the way. I just know from living on campus for the last 30 years what the net mask is. Or I could take 255 and subtract 3, and I still wind up with 252.0. So when we do the CIDR address or the net mask address, they're completely equivalent. It's just a difference in notation. It's a different way of explaining how are we going to assign these things. One thing that's really important to note, the internet does not allow fractional addresses or non-contiguous networks. So if I had a net mask of, say, 255.252.128.0, that is not allowed. And what this is saying is I would have like the first 8 bits, and then the next 6 bits, and then a bit, and then a bunch of zeros here. And then that's going to somehow be the hierarchical assignment to a subnet. The routers can't do that. Those are just not valid subnets. And that's why it just makes sense to use this CIDR abbreviation. If we could allow this kind of subnet for some reason, then CIDR wouldn't work because I wouldn't be able to say which of the bits were set. But this is not allowed. The only thing that we can do is we can take an IP address and we can turn it into 3 sections. The global net number, there's a section of bits for the subnet and a section of bits for the host. And they have to be in that order to maintain a hierarchy. So I can use this to decide our 2 machines on the same network. So for example, if I take so there's 2 ways to answer that question. So the question is, are these machines on same subnet? And I can answer that question by simply looking at the network mask. So 157.160.36.4 and 157.160.37. Let's make it more interesting. We can make it really interesting. 39.8. So in order to know this, the question is going to be, are their network numbers the same? And the network numbers, or in this case the subnet numbers, are going to be, if I take the network mask or the CIDR address, do I get to the same number after I turn off the bits that are not part of the network number? So let me rewrite this just for a second down here because I'm going to be out of space. 157, 160, 39.8. If you want to hit pause in the video and see if you can calculate what this is going to be in binary, or the relevant parts of this in binary anyway, go ahead and hit pause and see if you can come up with the binary numbers and see if they're the same. And then once you have that, then see if you can do what I'm doing here. So now that we've done that, we know that our network number here is /22. And so that means these guys are always going to be the same. This thing is going to be a 36. So that's no 128, no 64, a 32, no 16, no 8, a 4, no 2, and no 1. And it doesn't matter what comes after that. So I could care less about that number. What I'm really interested in is these first two numbers. And if I turn off all of the rest of these, turn those off, then the number I'm left with is 157.160.36.0. And that's the network number for the School of Engineering. If we do the same trick for this entry, I still get 157.160. Now 39, I'm going to do it down here. 39 doesn't have a 128. It doesn't have a 64, but it does have a 32. It doesn't have a 16. It doesn't have an 8, but it does have a 4, a 2, and a 1. Right? 32 plus 4 is 36, and 2 is 38. 1 is 39. But as we just said, we turn off the lower two bits. They go to zeros. And so what I'm left with is this number, which is 36. And since the two network numbers are the same, these two addresses, even though they look pretty far apart, are on the same subnet. They are local to one another. They do not need to be routed. They do not need to be forwarded. So that decision right there is the routing decision. And the goal of all of this is to be able to do that as fast as possible, because we're going to have to do it for every packet that arrives on a network. So CIDR can help be a shorthand for expressing these long net masks, but you should be able to go back and forth between a CIDR net mask or CIDR and a net mask representation pretty efficiently. So again, let's just pick an example off of this guy. Let's try a CIDR notation of 28. So with 28, that means I have 28 bits for the net mask. And so my net mask is going to be 2, 3, 4, 5, 6, 7, 8. There's 8. 1, 2, 3, 4, 5, 6, 7, 8. There's 16. I need to get to 28. 1, 2, 3, 4, 5, 6, 7, 8. There's 24. I need 4 more bits. And so that's going to be 1, 2, 3, 4, followed by 4 zeros. So our net mask is going to be 255.255.255. A 128, a 64, a 32, and a 16. Or I could do 255 minus an 8, a 4, a 2, and a 1. So this is an 8, a 4 is 12, 2 is 14, 1 is 15. 255 minus 15 is 240. So this net mask would be here 255.240. So they are completely interchangeable, and what you'll find is whatever organization that you're working with, you probably only have to do that mental calculation 1 or 2 times before you just recognize the CIDR rules and the net mask numbers that are here on your location. I mean, like I said, I just know from being here and doing networking for so long that the CIDR for ship subnets is 22, the CIDR for campus is 16, our net mask is 255, 255, 252.0, or for campus would be 255.255. If I was on another, like at home, I'm on a 24-bit subnet on my local side, so that would be a /24. and that gives me 255.255.255.0. And what Comcast gives me is a single IP address.